Hello everyone and welcome back to PC Retro Programmer. In the past couple of videos we've been looking at the problem of drawing a general ellipse. So this is a standard ellipse, one in standard orientation, that's been rotated through some angle. And we want to draw this on very early PC hardware, in fact with an 8088 CPU, and we're going to do it in assembly language. Now in the previous video we figured out a few things about the equation of the ellipse. We started off with the equation of a general conic. It has these 6 constants a through f, and they determine the shape of the conic. And it turns out that if b squared minus 4ac is negative, then we get an ellipse, a general ellipse. And we also discovered that if you center this ellipse at the origin, then there's a kind of reflection, a symmetry that this ellipse satisfies. And if you factor that in, you can actually get a simpler equation for the general ellipse with just 4 constants, a, b, c, and f, that control its shape. And then we went through and computed 8 points on this ellipse. These are going to be the starting points of 8 arcs that we're going to use to draw the ellipse. We discovered when we did the standard ellipse that if you're drawing an arc that's always moving more north than any other direction, or say more northwest than any other direction, and so on, then it'll be easier to draw. So we need the starting points of the segments that are headed more north than anything else, more northwest than anything else, and so on. And we used a little bit of algebra to calculate those 8 points. So there's 2 points for each of 4 cases. And in today's video, what I want to do is to update you on some progress I've made in coming up with a plan for actually computing these. Basically, once we've computed these 8 points, then it's pretty straightforward from there. Everything just turns out to be integer arithmetic using a standard algorithm that we already developed for the standard ellipse, just with different starting points and constants. So the real key is actually computing these 8 points. So let's take a look at what we can figure out about the values that we've got to compute here. So first of all, it turns out that when you plot a general ellipse, the only values that really matter are a, b, and c. When you actually do the computation with integer arithmetic, the algorithm actually only relies on those 3 values. And in particular, these values, you want to take those as integers, because then you can do integer arithmetic on the machine. So we really want a situation where a, b, and c can all be integers and still have enough control to make the ellipse any shape that we want. So that's going to be our strategy basically. And in order to do that, we need to know a little bit about what sort of integers these can be. Can they be positive or negative? Can they ever be 0? And so on. So let's take a look and see if we can figure some of that out. The first thing that we can do is we can look at this equation here, and we can say that if I just multiply the whole thing through by a constant, that won't change any of the xy values of the points on the curve. All we'll do is just multiply all the constants through by that constant. And so you can imagine, for example, if I just multiplied all of those constants through by 2, the right hand side would stay 0, because 0 times 2 is 0, and basically nothing else would change. All the same xy values would still satisfy the equation. And similarly, if I multiply through by -1, then this equation will still describe the same ellipse. And that's really cool because it means that I get to choose the sign of one of these constants. For example, if a was a negative value, we could just multiply the whole thing through by -1, and then a would be a positive value. So let's do that. Let's choose a to be a positive value. Now we can ask about some of the other constants here. For example, what about c? And it turns out that if you look at the discriminant here, this is a value that has to be negative. Let's suppose that A was positive and C was negative. That would make this term negative, which with the minus sign here would be positive, and B squared is either 0 or positive. You can't really have a positive value and a positive value giving a negative value when you add them together. So it turns out that C can't be negative. C has to be a positive value if A is. So that's now two constants that we know something about. Now B unfortunately can be positive or negative. You can see that we square it in the discriminant, so it wouldn't really matter if it was positive or negative, you get the same thing. So there's nothing we can really say about the sign of B. And F is a little bit more complicated, but it's not too bad after the algebra that we already did in the previous episode. We computed these 8 points here, and if you just look at this coordinate here, we know that these represent actual points on the ellipse. In other words, these square roots must be real values. They can't be complex values. And so what that means is that the value inside the square root has to be positive or 0. Now we know that the discriminant is negative, and so that means that the numerator here has to be negative as well. Otherwise we'd be taking the square root of a negative value. And we already know that A is positive, so that means that F has to be a negative value. So always F is negative. So now we actually know something about the sign of 3 of these values here, which is pretty cool. Now the other values that I'm a little bit worried about are these values here, the A plus B plus C and A minus B plus C that occur in the denominators here. If those could be 0, then we'd be dividing by 0. But let's take a look at this value here. Supposing A plus C minus B was 0, then A plus C would be equal to B. And if we square both sides, we get a B squared on the right hand side. And then I can actually subtract the discriminant, which has also got a B squared in it, and get rid of the B's. And I'm just left with something with A's and C's. It's actually a quadratic equation in A and C. And if I write it down and look at it, I'll notice that it actually basically now says that A minus C squared equals the discriminant. Now A minus C squared is either 0 or positive, and our discriminant is negative. So we have a contradiction again. So this means that basically this value can't be 0. And exactly the same argument shows you that this value can't be negative either. So this denominator here actually has to be positive. And it turns out that exactly the same argument will work for this denominator as well, and shows that this denominator always has to be positive as well. So that's really cool. Being able to use positive values in computations is a lot of value because we don't have to set aside a bit for the sign. And so this means we have one bit of extra precision when we're computing things, which can often be the key to getting a really fast algorithm. Now I will have to analyze these other values that can occur here, and you can see that they're squared, so very likely those can be positive or negative, but it might not actually matter. Given that we are going to square them anyway, we can do that and then just end up with a positive value and then just not think about it anymore because we can deal with it all with positive integer arithmetic. So things are looking pretty good as far as computing these values. If these are all basically integer values that we're working with and then just taking a big square root at the end after we've done the division, then it looks like we only have 2 parts of this that are even going to involve floating point or fixed point arithmetic, namely the division and the square root. Everything else is just integer arithmetic, and we just need to keep in mind that the discriminant and F are negative, and that's really easy to deal with. So I still have a few concerns though. The first is, how big can these integers be? And so that's something that I want to look at, and I'm going to do it by actually using some graphing software that I showed in the previous video, and we'll try and figure out a little bit about what happens with these values, how big they can actually get. So let's take a look at that. Before we jump right into analysing the arithmetic, let me just show you something really cool that I discovered while I was fiddling around with this software. This is the desmos.com/calculator software, and it allows us to draw an ellipse here. So I just put in the equation of an ellipse, but what I did in this experiment is I rewrote b in terms of the discriminant, which I'll just call d here, and ac. So remember that the discriminant d is just b squared minus 4ac, and if you rearrange it, you get b is the square root of d plus 4ac. And when I do that, what this allows me to do is to just vary a and c, and I'll keep the discriminant constant. And what that's going to do is it's going to adjust b such that the discriminant will always remain constant, and then I can just vary a and c. Now, first of all, if the discriminant is positive or 0, I get a hyperbola. We already knew that. You have to have a negative value for it to be an ellipse. So let's see what happens now if I leave the discriminant constant and allow it to adjust b to keep that discriminant at minus 4.2, and I'll just vary a and c. Well, first of all, when I vary a, what happens is it skews the ellipse in the vertical direction. You can see that this point here and this point here don't move, and the further you away from the vertical axis, the more it skews the points up and down. And you can see that this is basically just a skew of a standard ellipse. There's the standard ellipse there when the b value ends up being 0. So that's really cool. What about c? Well, would you believe it? It does the skew in the horizontal direction. So you can see that this point and this point now remain constant, and it skews in the horizontal direction. So that is really cool. We've actually found, by accident actually, the relationship between skew ellipses and general ellipses. Basically, the skew ellipse can be rewritten into a general ellipse where b is taken to be this value here, keeping d constant. So that's really nice. Anyway, this is not going to be useful for our project, but let me show you what I did for the general ellipse. Now, in order to play with a general ellipse, what I decided to do is to start off with a standard ellipse, like the one that you see here, and then just apply a rotation to it. Now, a standard ellipse has a very simple formula. It's 1 on r squared times x squared plus 1 on s squared times y squared equals 1. And so in terms of our constants for a general ellipse, that's a equals 1 on r squared, b equals 0, c equals 1 on s squared, and f equals minus 1. You can see I've set f equal to minus 1 here on a slider so that we can play with that. And I've also got this r and s that I was talking about. And these actually turn out to be the semi-major and semi-minor axes. So for example, r is this length here. If I fiddle with that, you can see it changes the width of the ellipse. And s is this height here, and you can see that if I fiddle with that, I can change the height of the ellipse. Now, I set this up so that r is 160 and s is 100, which is exactly half of the width and height of a CGA monitor in pixels. Remember, it's 320 resolution in the horizontal direction and 200 in the vertical direction. So this is actually the largest ellipse that we could draw on a CGA screen. And now I'm going to apply a rotation to this, and that's what this d value will be all about. I wanted to use theta for the angle, but it actually interprets theta as a variable, not a constant, and I wanted to set up a slider with a constant that I can vary, so I had to call it something else, and I just called it d again. This is not the discriminant, it's an angle. Think of this as angle theta, and I set this up to go from 0 to pi on 2, and you can see as I change that, it'll change the rotation angle. So how did I actually do this? Well, it turns out that there's a very simple way to rotate a point about the origin in the plane. And basically all I need to do to rotate an ellipse is just rotate all of the xy coordinates of points on the ellipse by some angle theta about the origin, and that rotates the ellipse. And the formula is very straightforward. You can find it on Wikipedia. For example, look on the page on rotation matrix, and it tells you that what you have to do is take your point xy and replace x with x cos theta minus y sine theta, which I did up here, and replace y with x sine theta plus y cos theta. And that's really all there is to it. That will change all of the xy points by rotating them by this angle theta about the origin. Now, this is what we eventually want to do. We want to actually specify our ellipse as a standard ellipse with horizontal and vertical semi-radii and an angle theta that we want to rotate it by. Now the question is, what a, b, c and f values is that going to correspond to in our equation for a general ellipse? And it turns out to be fairly easy to work out. F will just be minus 1, as I said, and to figure out a, b and c, I just need to expand out these squares in this formula. And if I do that, I'll get expressions in x squared, xy and y squared, and then again in x squared, xy and y squared, and I can just group like terms together. The coefficient of x squared is a in our formula for the general ellipse, and when you work it out with some algebra, it just turns out to be this value here. This is the coefficient of xy, our constant b in our formula, and it just turns out to be this value. And the coefficient of y squared is our constant c, and it's this value. And this program is really neat. You can just click in the left hand side here and set up anything you want in here that you want to monitor, and it'll actually show you the values changing as you fiddle with the sliders. So for example, if I change this rotation angle here, you can see the a, b and c values are just changing. So that's really cool. But you can immediately see a problem. We want a, b and c to be integer values, and you can see that these are tiny values here. If I had to pick the nearest integer, these would all be 0, and well, nothing would actually change. So obviously I really don't want values this small. Now, the only way around this is to multiply all the constants in our equation through by some really large value so that all three of these become large enough to be integers. Now they won't be exactly integers, of course, but we can round them off to the nearest integer. And what I want is that these integers are large enough so that when I round them off, it doesn't change the shape of the ellipse very much. It's just such a small, imperceptible change that you wouldn't even really notice it on a monitor. So these need to be, reasonable sized integers. They can't all be 1, for example, or 1 and 2, so that there are only 2 different possible shapes that we can draw. They need to be of a reasonable size. And so I found that the way to do this is to multiply everything through by a factor of 560 million. That seems to be a reasonable value. So that means that all our constants will be multiplied by that, including f. So this will now become minus 560 million. So let me go ahead and make that change here, and then we'll take a look and see what we end up with. So I've gone ahead and done that. The main thing that you have to do is just click on these, and then you can actually set the range that's allowed. And so I just set a range of 1 billion here. So now I've made f equal to minus 560 million. And you can see that the S and R values now have to be very, very small in order to get an ellipse of 160 and 100. I don't quite have exactly the control I'd need here to get those to exactly those values, but that's close enough. And now this angle theta here, when I change it, you can see that the values of A, B, and C are all quite large. And in fact, they remain basically small enough to fit inside a 16-bit integer. And in particular, if I change just by the smallest rotation value possible, take a look at what B does. I go from the first point on the thing to the second point on the slider. You can see that the shape of the ellipse didn't change at all, and yet B changed to a value of 622. In fact, if I go all the way out to this end, B is 49, it's not 0, and well, I can't tell that that's not a standard ellipse. So it looks like we get the kind of resolution that we want in the values, and we could round these off to integers, and it just wouldn't make any difference at all in the shape. You wouldn't be able to tell. So this seems to be a good setup. Now R and S end up being very, very small now, but this is not really a problem because R and S will only be used in the very, very initial part of the computation used to figure out what the A, B, and C values should be to start everything off at. So it doesn't really matter what size they are. And that's really cool. It means that we now have a way of dealing with the arithmetic here so that we can actually pick A, B, and C to be integer values. Now, as you can see, f ends up being very, very large, and f is basically around about the size of the largest integers that we'll need to actually play with in the algorithm, as far as I'm aware. And so that means that we'll need to be dealing with integers that are 32 bits. A billion would be a 32-bit value. I think you can go out to about 4 billion or something like that. And so that means that we need to use 32 bits for f, but we can probably use 16-bit values for A, B, and C. And that's going to work really well on a 16-bit CPU like the 8088 is, or at least it's 16 bits internally in terms of the register size. So that's going to be great. Of course, we still have a little bit of work to do. We need to actually do some experiments and confirm that for every kind of ellipse that we want to draw, we're going to end up with values that actually fit within 16 and 32-bit values. So I'd actually have to implement the algorithm in a very, very fast programming language that basically allows me to go through every possible ellipse I could draw and check that the values never overflow. And I think that's what I'll do before I make the next video, which will be in probably a couple of weeks' time now. The other thing that I want to note here is that these values that I'm going to end up with here, these A, B, and C values, are going to be positive values, except for B, which can be negative. Now that's one little fly in the ointment, because you can see that as I go through the values here, I might end up with a value. It doesn't look like it here, but it might be possible to end up with something that's a little bit too large to represent as a 16-bit value if it's signed. The other problem is that the algorithm itself is actually going to use various combinations of these values. I think the worst one is something like 2a plus 2b plus 2c. So it probably isn't going to be sufficient to work with f quite that large. We might have to make it a little bit smaller just so that 2a plus 2b plus 2c fits inside a 16-bit integer. And that is going to mean that the smallest values of b here could end up being a little too small. This might end up being, a much smaller integer, and that could be problematic in the end. So I'm not really clear if that's really going to be an issue or not. Let's say I had to make this 4 times smaller. Well, that'd be, something like 12, and I guess that's fine. So maybe we don't have to worry about that. But it does mean that I'm not going to be able to have a lot of individual steps in the rotation angle here. So basically I'm going to have to make the smallest rotation angle big enough so that I can actually distinguish the two values of b that I end up with. So that's one limitation that we're going to need, but we're working on a 16-bit machine. We have to assume that there's going to be at least some trade-off when working on such a limited machine. But so far, other than that, I don't really see any serious problems that we're going to run into. Even if I make S really small here so that I get a very narrow ellipse, or as narrow as I can go at the moment, then I still end up with values that are reasonable. Now you can see that what happens is the values become much larger. They won't fit in 16-bit integers anymore, but they're not far away from each other. And so that means that all I need to do in those cases is just scale f, make that smaller, and then I'll get integers that I can actually fit in 16-bit registers. So it turns out that there's always going to be a solution that works for us. These values don't ever end up being really radically different. I mean, even if I go right to the end of the scale here, I have, let's say, 6,000 compared with 4 million. So the difference between those is less than 1,000, and so certainly I've got enough resolution in a 16-bit integer to represent that case as well. I just have to scale by something other than 560 million. So it looks like everything's going to work out just fine. The idea will be to take the largest of the values that we need and make it fit into a 16-bit register, and then just set things up so that this f value can't exceed a 32-bit value as well. That would be the other restriction, and in fact I want none of the values that I have to work with in the algorithm to exceed a 32-bit value, and that's all there is going to be to it. So we've made some progress, and we'll see exactly what we need to do in the next episode, when hopefully I can write some code to exhaustively check all the ellipses we're going to want to draw and see what values we have to choose.